objects. In your syllabus, it is called connected objects. How are the objects connected? The objects, they are connected by a string, right? Wait a minute, So these are the two objects, one here and one here. These two objects, they are connected by a string over a smooth pulley. Okay, so this type of problem is called connected object in your textbook and also inside your syllabus. Now, before we continue with this type of problem where we have pulley and a string over it, you have to know something about this type of system. Now, for this type of system, the first thing you need to know, because it is moving, accelerating, you need to know Newton's second law of motion. What is Newton's second law of motion? F equals to ma, right? And what is this system called? This system is called connected objects. And for connected objects, we have one assumption. The assumption is number 3. Two bodies connected by a light string. This string is inextensible and it passes over a frictionless pulley. There are 3 assumptions here. The first assumption is the string is actually very light. The string or the rope used here has no weight. Because if it has weight, it will slow down the system. We cannot calculate unless we take into consideration the weight of the rope or the string. To avoid this type of problem, we say the string is very light. This is the first assumption. The second assumption is that this string that is used to connect the two objects, they are inelastic. That means the string here or the rope here, they cannot be stretched, right? So the cannot be stretched means inextensible cord. The cord cannot be extended. You cannot pull them and make them any longer, nor will they shrink and become shorter. Now, why they have to make this assumption? Because if you say the cord or the string is extensible, you are saying that the string is elastic. And if it is elastic, there will be elastic force inside it. You remember when we learned about this Hooke's law, if there's a spring and this spring is extended and they will produce a force and there will be potential energy stored in the spring. We don't want this type of thing to happen. So we say that the string is inextensible. That means you cannot stretch the string and produce an elastic force inside there. So that is the second assumption. The third assumption is that the pulley is frictionless. That means this pulley has no friction. Or it is quite important if the pulley can produce a frictional force, and we have to take into consideration the frictional force, the angle of friction, and so on, right? So this is the third assumption. So altogether, there are 3 assumptions. 2 about the rope and 1 about the pulley. Okay. You read this example 4.13.
Two objects of mass m1 and m2 with m smaller than m2 are connected by a light and extendable cord and hung over frictionless pulley as in figure 4.38a. Both cord and pulley have negligible mass. Find the magnitude of the acceleration of the system and the tension in the cord.
Okay, right. Uh, two objects of mass m1 and m2. The round one is m1. The square object is m2. M1 is less than M2. M1 is less than M2, that means the M2 will win. The M2 win, that means the system is moving in the direction of M2. M2 is heavier, so the whole system on this side will move downwards. The whole system will move, here will move downwards on this side because M2 is heavier. But on the other side, M1 side, because M1 is lighter, it will move upwards. Okay, so we say that the M2 is accelerating downwards with an acceleration of A2. M1, because it is lighter, it is accelerating upwards with an acceleration of A1. Now this A1 and A2, you cannot say that they are equal. You know why? Because A1 is going upwards, A2 is going downwards. So they are moving in different direction. Acceleration is a vector quantity. If you say the two of them are the same, that means they must not only be, the magnitude must not only be the same, the direction also must be the same. But in this case, the direction is different. So we cannot say that A1 equals to A2. However, we can say that A1 is equals to negative A2. Okay. Or we can say that the magnitude of A1 equals to the magnitude of A2 and is equals to A. Right? So in other words, the whole system is rotating clockwise. It is rotating clockwise with an acceleration of A. Right? We don't talk about the direction lah. We just talk about the size of the acceleration. The size of the acceleration is A. Right? This one. The size of the acceleration is A. The size of the direction is A. But if you want to look at the individual acceleration, you have to call them A1, A2. The reason is because the direction is different. Now, we look at this, the force diagram. The force diagram of this system. Right. Now, when we look at the force diagram and the overall system as a whole, the system is rotating clockwise. Can you see the red arrow here? It is rotating clockwise with an acceleration of A, magnitude A. If you look at the system as a whole, you don't have to consider the tension in the string, because the tension in the string, they will cancel each other. So we only look at the forces acting on the system. They are M1G and M2G. M1G is asking the system to come anti-clockwise. M2G is asking the system to, the pulley to rotate clockwise. Okay, so far, is it clear or not?
Understand, sir.
Okay, so one is rotating, one force is asking it to rotate, asking the pulley to rotate anti-clockwise, clockwise. So that force is M2G, the rectangular block. Another force is asking, hey, don't go clockwise, you come with me, you go anti-clockwise, and that one is the M1G. Who will win actually? Who will win? The M2G will win or the M1G will win?
M2.
Correct. Because M2 is heavier, so M2 will win. So we start by writing M2G minus M1G. Okay? we start by writing M2G minus M1G. Because M2 is bigger, it will win, right? Because it's bigger, so we start with M2 minus M1. And that will be the net force. So the net force is M2G minus M1G. What is the net force? Net force is actually the mass times acceleration. But in this case, the mass is of the system is M1 plus M2. The mass of the whole system is M1 plus M2. So because the whole system is rotating rotating clockwise, so we say that M1 plus M2 times A, that will be the net force of the system. And that net force is M2G minus M1G. There's a common factor here. The common factor is G. You can take out the G, right? When you take out the G, this G here, so what is left is M2 minus M1 bracket G. If you want to find the acceleration of this system, what is the acceleration that is rotating clockwise? That direction will be M2 minus M1 divided by M1 plus M2G. That will be the acceleration of the system. And this is obtained by considering the system as a whole. The tension, they cancel each other, right? Any questions so far?
No question, sir.
No question. Now, if there's no question, we want to find out how much is actually the tension in the string or the rope here. String better lah, because rope is very heavy. It cannot be light and extensible anymore. So I call it a string. How much is the tension in the string here? Right? You can only find out the tension in the string when you consider the individual objects, not the system as a whole. Earlier on over here, we consider the system as a whole. So the tension doesn't exist. The tension, they cancel each other. Now, I'm going to look at one particular object. This particular object is M1, right? So when I look at M1, this M1 here, there are two forces acting on this M1. The two forces, they are tension in the string and the weight of the object. And the weight of the object, M1G. I'm looking at M1 alone, not the system as a whole. Now, can you tell me the net force is which force minus which force? There are only two forces here, T and M1G. Which direction is the object moving? Which direction is the object moving?
Up.
Up, correct. So if the object is moving upwards, which one will win? T1 win or the M1G?
T.
Correct, T will win. So if T win, I will use the T minus M1G. So the net force is T minus M1G. I'm going to change the net force into MA. So MA now, because I only consider one object, the one particular object, so the net force is actually M1 only, M1 times A. So I change the subject of the formula, make T the subject of the formula. So what is T? T is mg plus m1a. So it's m1g plus a. You can actually stop here already, g plus ma. But because earlier on we found out a to be this monster here. So I replace the A here with the monster formula there. Okay, so simplifying this, I have the tension in the string is 2m1 m2 divided by m1 plus m2 g. So this is the tension in the string. Okay, you go through again, then you see you have anything you want to ask me.
I'm okay for now. I'm okay for now.
Okay, now if there's no question, then I want to summarize what we have done so far.
Okay.
For connected objects, objects that are connected by a string, there are two ways of looking at it. One way of looking at it is looking at the system as a whole. When you look at the system as a whole, you don't see the tension in the string, because the tension in the string, they will cancel each other. Okay, then there is another way of looking at it. You look at the individual objects in the system. Look at one particular object in the system. Either you look at M1 or you look at M2. So only then the tension will come in. Only then the tension will come in, right? So from there you can calculate the tension in the string. Okay, so two ways of looking at it. The first one, look at the system as a whole to calculate the acceleration. The second one, look at one particular object, calculate the tension. Okay? So this is the method that the approach that we are going to use.